Paging Andre. Andre, you come this way. Okay. Okay, this is one of Andre's students, so we're going to let him introduce him.
All right, folks, get inside. Come on. Awesome. All right, all right, all right. Cool, cool, cool. All right, you guys. There's one more seat, empty seat. Somebody's missing. Okay, so I've been referring several times to my students as my students. In fact, allow me to introduce the professors of these students who are in this room. Răzvan Ruginiș, who is the dean of the best IT university in Bucharest, Romania. And we're very honored to have him. And Răzvan Deaconescu, we have an inflation of Răzvan. So Răzvan Deaconescu, who is their advisor. Thank you. So allow me to introduce our youngest. Whose name is not Răzvan, is Alexandru. And Alexandru is, he's so young, I was a person before he was born. I had drama in my life before he was born. So that's why I said, this guy is really young. You know, before he was born, I had trouble in my life, existential, whatever. Young and good-looking and well-dressed too. So he's our youngest, but definitely not our weakest. His work is really, really interesting to our community. We've been at this for a while, and I think it's terrific. It's very interesting work on safe memory allocation. Give a hand to Alexandru.
Hello, everyone. This is my first year at DConf. And as Andre said, I'm going to talk about safe manual memory management. So when we think about manual memory management, of course, we're thinking about high performance, applications with low memory footprint, and of course, deterministic lifetime of objects. The garbage collector, however, should not be underestimated. So because we don't care about object lifetimes, this of course can lead to a huge increase in productivity. Also, this comes with the benefit of having safe code by means, of course, of safety checks, and of course, because we do not use memory after being freed. So these vulnerabilities are most likely the greatest downside of manual memory management. And we're talking about use after freeze, buffer overflows, double freeze, and of course these can not only lead to undefined behavior, but of course to a lot of security exploits. So in order to illustrate this, let's take a look at the following example. We have a point structure with two integers, a user structure with a car array and an integer. All right. First, we're allocating a point, doing some computation with it, let's say, and disposing of it. So for those of you who don't know, the allocator is just a wraparound malloc. All right. Later, we need the user object. We allocate it, do some stuff with it. But because we have an error in our program, we're still accessing the dangling reference to the point object. So what happens here? Well, one outcome is that the program, of course, crashes. Okay, but this is not always the case. So because allocators, such as malloc, need to be very efficient, what they do is that they reuse memory. So one outcome here is that the point object overlaps in memory with a previously allocated user object. So if this is the case, when we're writing the value 100 to x, what actually happens is that we're writing the value 100 on top of the car array from the user object. So worst case, this can lead, of course, to arbitrary writes in memory, memory corruption, and of course, very hard to debug issues. So, of course, this is bad, but we still want the high performance. So, in other words, we want to bridge this gap between the high performance of manual memory management and the safety which is offered, for example, by the GC. And one solution to this problem can come in the form of custom allocators. So have any of you used custom allocators before? Awesome, great. So hopefully this will give you a couple of ideas for your projects. So we want to create an alternative to the traditional malloc. An allocator which, of course, is usable in safe code by mitigating dangling pointers. Of course, it has to offer high performance, and it has to coexist with other allocators. More precisely, it has to be compatible with a garbage collector. All right. So in terms of related work, there are these two papers from Microsoft Research, from which I have drawn great inspiration, and I highly recommend you take a look at them. All right. So since this is a talk about allocators, I want to talk about how allocators from the allocator modules in D work. So an allocator is just a structure which first of all offers the allocate and the deallocate primitives, which gets a fresh chunk of memory and later freeing it. Optionally, it can provide aligned allocation, reallocation, expansion of previously allocated memory, and many others. Here are a couple of examples of allocators from the D standard library. So first, we have this region allocator, which gets a chunk of memory, and each allocation simply advances a pointer. So it's very fast. Another useful one is the bitmap block, which again has a chunk of memory and splits it into equally sized blocks. Also, it has some bitmap, which allows for quick scanning of freed blocks. More popular allocators are, of course, the GC allocator and the mallocator. The great thing about these allocators is that they can be put together like building blocks, like Lego pieces, in order to create more advanced allocators. So in this case, we're using the segregator, which depending on the allocation size, we can forward that to various allocators. So in this particular example, if we want to allocate 64 bytes or less, we're going to use the bitmap block on line 2, which has 64-byte blocks. Alignment of each block is 8 bytes. Again, if the size is between 64 and 128, we're going to use another allocator, which has 128 blocks, each aligned to 16 bytes. If the size is greater, just forward everything to the mallocator. Okay. So now that we have a better understanding of what allocators are, let's take a look again at this example. So the problem here was that we were accessing the dangling reference to the point. If the program crashes every time when we access this, then there is no problem. We have an error and we get deterministic crashes. So the problem here comes that the point object could overlap in memory with another object, for instance, the user one. In other words, the problem here is that reusing memory is not safe. So we have to create a mechanism to not reuse memory. And one idea is to always allocate at increasing addresses. And for 64-bit systems, this is great. On 64-bit systems, the address space is virtually inexhaustible. This may or may not work on 32 bits, but I'm going to focus here on 64-bit. So I recently added to the allocator modules the sending page allocator, which does exactly this. First, this maps a large chunk of virtual memory. So it's important to mention here that we don't actually allocate anything. We're just reserving a range of virtual addresses which have no permission set. So any access to this memory results in crashes. For those of you who are interested, on POSIX systems, we're using the mmap family of functions, and on Windows, virtual alloc. I'm not going to enter into too much detail about the actual implementation, but if you're curious, we can talk after or during the questions. So how are we going to approach allocations? Just like for the region, each allocation advances a pointer, and we're going to set read-write permissions to the new chunk of memory. Again, another allocation comes, further advance the pointer, set the permissions. Okay. But how about the allocations? Well, first of all, we want the operating system to reclaim the physical memory. But what we don't want to do is we do not want to lose this mapping. So we reclaim the physical memory underneath, but keep this mapping with no permission set. And this is because we want any access to free the memory to result in deterministic crashes. Okay? So although a bit primitive, the ascending page allocator is safe. Any access to freed memory results in deterministic crashes. Because we're using operating system primitives, each allocation is rounded to a multiple of the page size. And if we're talking about large objects or huge arrays, then we're going to be all right. Wasting a couple of kilobytes may not be such a big deal. But let's say, for instance, that we want to allocate 16 bytes. Well, obviously, it won't work. We'll have very high fragmentation. So let's try and improve this a bit. So for the particular case of 16 bytes, we're going to allocate from the ascending page a huge chunk. Again, I said 2 megabytes, but it's not mandatory. It's just an example. So we're going to allocate this huge chunk and split it into equally sized blocks. Again, we're going to have somewhere in here some metadata in the form of a bitmap to help us tell which blocks are free and which aren't. So each allocation will return the next block available. If we run out of blocks, again, create another chunk, split it into smaller blocks, return the next one available. So allocation is simple, return the next block available, and again, without reusing memory. All right? But how about deallocation? So given a block, which we have to deallocate, a 16-byte block, we want to find, as quickly as possible, the large chunk, the large green chunk, to mark in its metadata that this block is no longer in use. So the question for you is, how can we find the huge chunk as quickly as possible, given the 16-byte block? Any ideas? Yeah, sure, Dimitri.
Well, you can align your memory mapping to like 2 megabyte granularity, and then you just do a shift, and this is your offset.
Excellent, yeah. Yeah, so the first thought is to iterate through all these blocks and check for each one if it contains the 16-byte block. But of course, if we have a lot of these, it can be a bit inefficient. So the trick here is to allocate each huge 2 megabyte chunk at an alignment of also 2 megabytes. So now, given a block that we want to deallocate, we simply take its address and round it down to the nearest multiple of 2 megabytes, finding in constant time, deallocating basically in constant time. I also added this recently to the allocator modules. It's called the align block list. And it has these huge blocks in a linked list, each being managed by another allocator. In our instance, some variant of the bitmap block. And because the length and alignment of each block are equal, then we're going to have fast deallocations. Okay, so far in our design, we can already distinguish a couple of allocators. So each green chunk is some variant of the bitmap block. In our case, let's call it the safe bitmap block, because we don't reuse memory. Each block, the blocks are linked in a list. This is the line block list. And all of these draw memory from a root allocator, which is the ascending page. And now, to use the building blocks property to properly define this, so we're going to get this. If we want to allocate 16 bytes or less, we're going to forward the allocation to an align block list, where each chunk is managed by a safe bitmap block, draw memory from ascending page, and length and alignment is 2 megabytes. For larger sizes, just forward directly to the root allocate, to the ascending page. So for the particular case of 16 bytes, this will work perfectly. But what if we want to support other block sizes? Let's say, make it more general, support 32 bytes, 64, and so on. So any ideas how we can change this code to support also other block sizes? Yeah. Sure. Yeah, so we're going to use we're going to just copy paste that line basically, and now, but change the block size. So if we want to allocate between 16 and 32, we're going to use a different align block list. This one has a save bitmap block with 32 bytes, and so on. Between 32 and 64, another line block list, and so on. Question?
The ascending page allocator there is a pointer, so I'm assuming it gets allocated by someone. Who?
So we're going to have this somewhere declared at the top level. Let's say maybe it has a global state. And what I didn't include here, we have to write a couple of lines for initialization. So we have to link each one of these to that particular instance. Yeah, okay. Good question. All right, so although this definition may be a bit long, it's important to notice here that each line has a bit of meaning to it. So if we're doing a lot of allocations of 64, let's say, maybe we want to have larger chunks. But if we're doing very few 128 allocations, then maybe to reduce fragmentation, we'll have a smaller chunk size. So the idea is that it's highly customizable. So now let's see it applied to our example. We're going to declare it somewhere at the top level, initialize it, and the changes are minimal. Simply replace the allocator with the SafeAllocator. And now, when we're accessing the dangling reference to the point, it's safe. There are only two outcomes. Either the point is part of a chunk which is still in memory, and in this case, the damage is contained. We're making sure that we're not changing any other object. We're just changing that pointer object, which is still in memory. And the other outcome is that the chunk which had the point is no longer in memory, and we're going to get a crash. So the first iteration of the SafeAllocator, because it does not reuse memory, it's safe. We cannot corrupt our memory and have undefined behavior. However, it has a couple of problems. First of all, because we don't reuse memory, we're going to have high fragmentation. Also, because we're always going at ascending, but increasing addresses, it's very likely that we'll have a lot of page faults. And page faults are very slow. And in some benchmarks that I conducted, for small allocations and for very large allocations, the performance was very close to malloc, for instance. But if we have, let's say, medium-sized allocations, then it will be more likely to have page faults, therefore it being slower. Okay. So not reusing memory is safe, but a bit inefficient. Let's go back to the drawing board and see how we can fix this. So the problem here is that the point object can overlap with the user, and therefore we can corrupt our memory. And although the next question may seem a bit weird, but which other object would you want the point to overlap with? Which type would you want that object to be? Sorry? Yeah, sure. So it makes sense that if the point overlaps in memory with another point, when we're accessing P here, we still have the guarantee that we're modifying a valid point. So this is, of course, a bug and a different safety guarantee than before. But we know the type of the object which we're accessing. And this highly depends on the safety guarantees that you want for your application. All right, so the idea here is that instead of not reusing memory at all, we're going to reuse memory only for objects which have the same type. And for this, we're going to have for each type a separate arena. And all of these arenas will draw memory from a central allocator, which would be an ascending page allocator. So the thing here is that it's all right to reuse memory inside each arena, but we don't want to have two overlapping arenas. So that's why each arena will draw memory from an ascending page allocator. All right. So the changes to reflect this are minimal. The SafeAllocator now has to receive as a parameter the type of the object. And again, we're going to recycle the design and use the line block list. But it's important to notice here that in the previous case, we were using the safe bitmap block. But now it's all right to reuse memory, so we're going to use the regular bitmap block. All right. Now let's see it apply to our example. But first of all, we're going to define this helper function, getSafeAllocator, which helps us create basically this mapping between the type and its corresponding arena. The trick here is to declare the allocator in the static storage. We also benefit of lazy initialization, and in the end, we're going to return a reference to this allocator. Now, to our example, we're going to get the allocators for the two distinct types. And it is now clear that the point and the user draw memory from separate arenas. So there is no danger in them overlapping. Worst case, the point overlaps in memory with another point. Of course, we're going to have a bug by changing another point somewhere in memory. But this is still safe because we know the type of the object which we're accessing. There is no risk in corrupting the memory, for example, arbitrarily writing in memory. And it depends on the guarantees which you want for your program. Okay. So another great thing about this function here, the getSafeAllocator, as you may know, the static keyword defaults in the D language to thread local. So this function, in fact, is thread safe. And each thread will have its own separate copy of the SafeAllocator. Okay, and if we pay a closer look, we can see that the only global state which we have is this root allocator, from which everybody is drawing memory. So if we add synchronization to this, we can make the whole thing function in a multi-threaded environment. So again, with minimal changes, replacing the ascending page with its shared version, now the whole allocator is thread safe. So the second iteration is still safe, a different safety guarantee, but we're not corrupting our memory. As we will see in later benchmarks, it will provide high performance and it's scalable. But this still has one problem. So if our program has a lot of types, then most likely we'll have high fragmentation. We've come a long way. So first we had the ascending page, which although simple, was safe, but inefficient. Later we improved it. We added the align block list and increased the performance. We went even further and started reusing memory among objects of the same type. So what can we possibly do more to improve this? And to quote most of the characters from my favorite series, Dragon Ball, this isn't even its final form. So there is still one idea which we can apply to this. Let's take a look at the following two structures. So a point with two integers and an interval with two integers. So aside from the context in which these may be used, in terms of layout in memory, is there any difference between these two? No, so they're identical. So if the point would overlap with an interval, let's say, when we are accessing the X member, we have the guarantee that we're modifying a valid integer, which leads us to the next idea. Instead of reusing memory only among objects which have the same type, we're going to reuse memory among types which have the same memory layout. Again, the safety guarantee is even lower, but this highly depends on what safety guarantees you want for your application. So in order to achieve this, we're going to introduce the layout template. The layout template will receive a type and will output a list of offsets and members. So for the point object, offset 0, an integer, offset for an integer, the size of the whole thing is 8. For the user, offset 0 car array, 16 integer, and at least on my machine, the size was 24. All right, so these two structures, the user and the stock structure, let's say, have the same layout, the same memory layout. So we will reuse memory between objects like this, right? Again, different safety guarantee. But we know the type of the underlying thing that we're accessing. But how about these two? Are they still layout compatible? So the difference is that the user structure is aligned to 16 bytes. Everything is similar, but the size is now changed to 32 bytes. So the question is, are these still layout compatible? And the answer, of course, it depends. So if for instance, we put every object in a 32-byte block, then the members overlap perfectly, and they are compatible, let's say. We don't care about the extra padding at the end. But if, for instance, we're using different block sizes, then, of course, these are not layout compatible. And this is Andrei's idea with the layout, and he has recently started working on it. And we have to properly specify what does it mean for two objects to be layout compatible. Right. So in order to apply the layout technique to our allocator, again, minimal changes. Now the helper function, instead of passing the type, will pass the layout of that type. And the SafeAllocator will be parameterized not by the type, but by the layout. And with minimal changes, we still have fast, thread safe, and SafeAllocator. So in terms of benchmarks, I have conducted a series of allocations and deallocations, repeated a very large number of times. And in a multi-threaded environment, and on the left side, I'm doing allocations of single objects, and on the right side, allocation of array of objects. So for objects which have of size 16 bytes, we can see that malloc slightly outperforms us, but since we're talking about millions of allocations, the difference is not that significant. However, for array allocations, we can see that at times we even outperform malloc. For 64-byte, however, the situation changes a bit. Again, for single object allocations, we are outperformed by malloc, but the results are still pretty close. But if we're talking about array allocations, we can see that not only we significantly outperform it, but we scale even better. For 512 bytes, the situation, the outcome is clear. We outperform malloc in both situations, and of course, we scale much better. Sure.
How did you simulate fragmentation in this case?
So for fragmentation, so I had these tests, of course, are artificial, and the results may depend on the memory patterns of your application. Since the environments, my tests are not actually real-world applications with a lot of types and a lot of behaviors, I didn't get any accurate results regarding fragmentation. But knowing about how other allocators work, for example, JMalloc, I know that fragmentation for them was a big issue. And I assumed, like comparing the algorithms and the behavior, I deduced that the fragmentation would be lower, depending on the safety guarantee that you want. All right, so again, these tests are artificial, and but they're a good starting point. They look promising, but of course, depending on what your application does and how you allocate your objects, the results may vary. So in order to summarize, we have devised 3 versions of the SafeAllocator, each one with a different safety guarantee. Of course, depending on the safety guarantee that you want for your program, we can expect different performance and, of course, different fragmentation levels. But it's important here to know that we're not going to, let's say, use only one of them. We can actually combine them. So if you have, let's say, critical objects, which you want for them to be safe, you don't want to corrupt them, maybe you will want to use for them the first version. If you have objects which are allocated and deallocated very quickly, you can use for them, let's say, the second or the third version. Okay, so in terms of future work, currently I'm working on a wraparound mechanism. So the thing is that when we reach the end of the address space, we don't have any more virtual memory, so basically we stop there. We're going to return null for each allocation. So a wraparound mechanism is currently under work. I'm also working on reducing the virtual memory usage, so not map one giant chunk at first, gradually map virtual memory. And of course, to have a better understanding, it's important to improve the documentation for current allocators. Since we just started on the layout, it's important to have clear specifications about what it means for 2 objects to be layout compatible. And again, decide on a method to offer various safety degrees by a SafeAllocator. And of course, to do more detailed benchmarks, again, regarding fragmentation, memory usage, and yeah. So before I end, I want to give special thanks to Andrei, who has been a great mentor and helped me with great ideas. And I also want to thank the D community, especially those who have reviewed my code and helped me with ideas. So thanks a lot, and if you have questions.
We have ample time for questions.
So what happens if you run out of pages to allocate? Are you reusing like previously used pages? Because I mean, the number of pages you can allocate is also limited.
So if we run out of memory, basically?
No, I mean, you don't really run out of memory, but at some point you sort of don't have any more pages to allocate because like the addresses you're incrementing.
Yes. So if we reach the end of the virtual memory? Yeah, so far, if we reach the end, then we have to invalidate the whole thing. So I'm working on a wraparound mechanism, and the idea behind it is that by the time you reach the address space, if you start using things right from the, so again, to reach the address space, I assume that you'll have to do a lot of allocation. And probabilistically, if you start again from the beginning, it will be not likely at all to still have access objects which were allocated at the beginning. So far, no wraparound mechanism, but it's under work. Yes, question here.
Just a related question. Did you try different page sizes? Operating system page sizes?
No, so I experimented with 4 kilobytes page sizes.
Okay, thanks.
Okay, thank you.
I have experimented with wraparound systems for memory allocations. And the problem is when you have a use case which uses a stacked allocation, it can be that you need memory from the very beginning of your allocation cycle when you want to roll back the stack. And if you have overwritten that, then you have a problem.
So this is about stack allocations, right? So this is for dynamic allocations. We're not going to interfere with the stack at all.
Thanks for your presentation. I think it's a pretty cool work. I just have a small comment that the address sanitizer, actually, if you run address sanitizer, it overrides the system malloc with their own implementation that does kind of the same thing, where the reuse of freed memory is it's not completely forbidden, but it's delayed until really necessary. So it kind of gets the same behavior, but of course with the downsides of malloc as well that you're working against.
Okay. Cool. Yeah, I'll look over that also. Thanks.
Thanks for the talk. I have a comment and a question, and the comment is that this is probably not going to work with pure, because if you allocate within a pure function, then at the end, when it terminates, you may be able to change the type, and so you may be able to get aliasing between mutable and immutable data, and then screw up. Yeah.
Yeah.
And I'm not done. The question is, how do you want to deal with types that recursively have pointers to themselves?
Pointer to themselves?
For determining the layout, because I think.
So if they have pointer to themselves?
Yeah. For example, just a singly linked list, right?
So if you allocate a structure with such an allocator, and you have pointers inside that structure, if those pointers are to memory which was also allocated with this allocator, then you will have the same safety guarantees. But if you allocate that with something else, then I cannot guarantee that it will be all right. So everything which you use, let's say by pointer, you have to allocate with this one to have the safety guarantees across all your program.
Yeah, that's a good point too, but my question was more like, how do you want to reflect the memory layout of such types?
Can you repeat, please?
How do you want to get the memory layout of such types, because it's not an array of...
memory layout for such types? So the first thing that we did with the layout is, if they are exactly the same, then we're going to reuse them. So yeah, you have
maybe let's take this offline.
Sorry?
Maybe let's take this offline.
In response to your first point, so the second point, I don't think the layout is going to be, so you say like struct list, in payload, list next, list star next, right? Is that the question? And
yeah, and then you have a struct list 2 that does the same.
Sorry?
And then you have a struct list 2 that does the same.
Yes.
And now you somehow need to have...
They'll be in different pools. If list 2 has a pointer, could you, that's going to also address your first point. Could you turn back to the user example, the layout of user?
Okay.
Yeah, that's good. So it's very interesting. You should mention the immutable versus mutable. Initially, I thought a car array and the string have the same layout. And then I thought, when my student is going to give this presentation, Timo is going to come with that question. So they have different layouts. So the layouts are considered actually a layout of user. Let's assume the user has a string instead of the car array. The layout user would be 0, different type, right? String, immutable car array. So that would be a distinct from stock. Two structures have identical layout only if the qualifiers are also respected for members with, for all members. So, yes.
I don't know that it matters too much, because you're still just writing or looking at I mean, the thing is, you're going to corrupt data if you have a dangling pointer. Whether you corrupt immutable data or non-immutable data, I don't know that it matters.
Well, if you corrupt immutable data, you will destroy assumptions that the compiler may make, and then you will lose memory safety. So, and And this can happen because you can allocate mutable data using this allocator, return from pure function, and at the boundary you can automatically cast it to immutable, and then you have a problem.
And by the way, sort of the top level layer, which we haven't discussed today yet, is, for example, layout user and layout of immutable user are distinct. So they'll go to different pools. Essentially, like all immutable objects are going to go to different pools than their mutable counterparts. And that's exactly for this reason you would end up corrupting immutable objects. I think there's one more. Johan? Walter?
One difficulty is if one of the fields is a union, and it's a union of like an integer and a pointer, then the new object, one may be a pointer and the dangling reference may be to an integer, so you could have trouble with that. And the only solution I can see to that is to have introspection disallow such unions for being used with this allocator. So
I think it's a great point. Also, like we could just confine to all distinct pools. Like layout of anything with a union inside is distinct from any other type.
Yeah.
So,
okay.
Yeah. Dimitri.
Well, I think we discussed this before, but well, I just could see the idea that you can like shadow the malloc free and realloc, and basically have like sort of memory safe C right there. Just a thought.
Okay. I tested the layout proposal that I think Andre uploaded to GitHub, and currently it will fail when you have a union anywhere, like the compilation will abort because it's not easy to introspect anonymous types. Basically, you cannot introspect anonymous unions or anonymous structs inside other structs, and that's going to be hard to fix, I think.
Just let me address this. Like, obviously we need to be able to introspect unions. So I consider this a distinct problem, not a fundamental problem. It's a matter of having the appropriate support in the language. So yeah, definitely, this definitely we can and we will do this.
Maybe one comment or question, like a typical thing in the server-side software thing is actually you have different users, and some users are allowed to see some data and some users are allowed to see other data. Okay. So if you reuse the allocation thing, that could possibly be used for an information leak and get things you are not supposed to see, because it's you somehow trigger a dangling pointer, and then you see like somebody allocated a new user information there, and then you leak the passwords of some, or like the hashes or credit card numbers from somebody else. So it's a weaker memory safety constraint than probably other systems are using.
Could you go back to the table you have at the end? The table. So one thing that Alex and I discussed, just literally before this, was
here?
No, the table. Yeah.
This one. Yeah.
So one thing that we discussed, and I think that is very interesting, is that versioning there is a bit misleading, because you would think that 3.0 is what you should use because the most recent, but actually it's you pick and choose. It's cherry picking. You get to choose what level of safety. For example, it's such an application that Martin mentioned, when you have a security risk of using, getting other people's read memory, you want to use 2.0 or 1.0, right? Or the GC, the hell with it. So you actually, that's the beauty of this project and the underlying allocators, is you get to really build your own. In literally like 5 lines of code, you have a high-performance working allocator with the trade-offs that you want, and you can change it with amazing ease. So I think, I think there is something to be said about the disadvantages of reusing layouts, reusing objects, reusing types, but those you get to pick and choose. One other possibility is, consider this. In debug mode, you use one allocator. In release mode, you use another allocator. And that's entirely possible. right? In debug mode, you have fewer optimizations. You can say, I'm going to splurge on memory because I want all my errors to be quickly detected, and so on and so forth.
What happens if the optimizer changes the layout of the structures actually used? I mean, the layout computes the layout at compile time, but if the optimizer then changes the layout, your structures might not actually have the same memory layout.
I haven't thought of that.
That couldn't happen.
Well, it could if the optimizer realizes that a member isn't used and then just removes it from the structure.
When you dynamically allocate, I mean, I've never heard of this. Like, you could deconstruct probably Johan has his hand like to the ceiling. Why don't you?
I think indeed if it's a private struct, completely local to a very small part of the program, you could optimize struct layout. But in general, if your structure is going to be used throughout your program, right, and then the optimizer will not optimize struct layout because it will pass out of it's very likely that the structure itself is going to pass beyond its view, right? And then someone else just has to use that struct, so the layout will have to stay the same. But in a local thing, yes, it can change, but I think then it's so confined anyway that it will already work.
Walter?
It would be a disaster if, in any case, introspection produced a different struct layout than was actually the struct layout. So I can't see that ever successfully working in a compiler for any purpose. So I don't think it's necessary to worry about that.
Questions?
Hey, thanks for the presentation. For the continuing one of the previous questions, yeah. So suppose you have a situation where you freed a point and then you created a new point on top of that, or like you have a dangling pointer to the old one, so you can see like old data. And suppose this was like a security critical situation. Is it possible for some of those allocators to zero out the memory as soon as something gets freed there?
So as soon as we free something to zero out the memory?
Or like fill it with junk or whatever, it would still keep it valid. I don't know.
Yes, yeah, it's possible. I didn't do that because of course it's slow. So,
yeah.
But
the
yes,
instructor may choose to do that actually, so
yes.
That's entirely possible.
Thanks.
I thought you're lining up a trap. Oh, in that case, boom. I don't know. More questions?
If I understand correctly, this is also working with a shared allocator?
Yes.
With shared?
Yeah, with a shared allocator, so the memory is shared between threads.
Yes.
And then the dangling object, or I'm not sure, is the same for different threads. Doesn't that produce maybe race conditions or even invalid state? So
yes, but if you care a lot about the shared objects, you can, for example, allocate them from something like the first one and make sure that no one will overlap with the shared object. And for all the other ones, use one of these.
No, they are, for the threads, they are local, but returned to the shared allocator.
I think it's a good point. It's a problem that we need to look at.
Yeah.
So essentially you're saying somebody has a dangling pointer in one thread, and another thread is legitimately using the same memory.
Yes,
right?
also as a dangling pointer.
And in that case, yeah. So I think we need to look at that, and probably we need to allocate distinct pools for distinct threads. So that's not difficult technically, but definitely something to look at. Thank you. Thanks, Rainer.
But this already happened. So each thread has its own pools. So the only danger is if you're actually allocating a shared object, and because the things you want to pass between threads most likely will be shared. So in this case, if it's not shared, then it's all right. You won't going to pass it anyway. But if it's shared, then, and it's important, use the first one, which is the safest.
Questions? Yes.
I find the idea interesting, but I would like to know how and where is this, how this situates comparing to reference counted, automatic reference counting, or this idea, because this was discussed a year or 2 years ago by the compiler, is this idea completely forgotten? And this is the other response to safe allocations or non-GC allocations, or
so these operate at, sorry, go ahead.
So if you have, so the problem that this fixes is that if you, for example, have a ref counted object and you leak outside of this ref counted object something, you know, so you have a pointer to something which was in the ref counted object, like have a structure and the pointer to something inside. So this could act like an underlying support for ref counted objects to get memory from.
My question is maybe more in a global strategy, as Apple has automatic reference counting added by compiler. Do the compiler will ever do some kind of this stuff, or not at all?
So, Andrei?
I'll take this in a second.
I just wanted to say that they're actually using normal reference counting because they have memory overhead problems with automatic reference counting in several locations, like particularly when allocating in loops and stuff like that. So maybe not so desirable to invest a lot of effort in something like that if we can do it like just with a normal library type.
So thank you for asking. I think this is. I meant to make a few closing remarks about this work. I believe it's a game changer in terms of addressing competitive pressure with memory safety. Such a safe allocator allows us to free memory with impunity and have efficient programs that are also safe with virtually no change in programming style or sort of no constraints on people using such an allocator. So I think it's strategically very important work. With regard to reference counting, we do plan to have reference counting data in the library. Reference counting for class objects is a possibility in the future. We don't have yet a concrete design, but they address different issues. So you have reference counting, which counts the number of references to the same memory, and then you have this allocator, which works underneath and ensures the safety in all situations virtually of memory use. So strategically, I think this is very important work because it's going to lay the ground for you can free memory in a safe code, period. And on top of that, we get to build any number of tools that assume that.
Just a short remark, because we are working with the systems which are actually quite limited in memory, and as I find this system interesting because it's a good idea, but I would this fragmentation part actually I would put high and moderate, more than high, moderate, low, in a sense of fragmentation, because from the experience. And especially when you think that you will need to allocate different pools for different threads, and fragmentation goes very high quite quickly. But it's maybe for PC or systems with unlimited memory, this is not a problem. But for spaces which are much more limited, this will be a big problem actually. So.
Definitely. To this, I'll respond by quoting a classic. Performance is to be found in the minds of people.
Any more questions? All right, Alex, thank you very much, and Andre. Okay, so let's go ahead.